Radioactivity is this phenomenon. A proton or a neutron will convert into a neutron or a proton respectively, and it will emit some radiations. There are three types of radiations. That can be gamma radiation, beta radiation, or alpha radiation, radioactivity. Natural radioactivity is all these isotopes we find naturally. It's potassium-40, for example, uranium, carbon-14. And it makes the natural radiation to a certain level. And because everything is radioactive, we are radioactive. Because we are made of carbon, we are made of potassium, lots of potassium, and we are radioactive sources, about, to give a number, 6,000 becquerel. So radioactivity is part of the everyday life.
So if it's natural, what's the fuss about nuclear radiation? What makes it so dangerous?
Typically, emitted radiation will interact with matter. And for natural radiation, alpha, beta, and gamma particles, the interaction is usually by a process of ionization. So we'll start with the heaviest. The alpha particle is doubly charged, 2 protons, and heavy. So it interacts strongly with all the electrons in the matter that it goes through and gets stopped very quickly. So a typical alpha particle's range in air is about 5 centimeters, but it wouldn't even penetrate a piece of paper. For beta radiation, which is an electron, it's much lighter and only singly charged, so it'll make it much deeper into matter. So a typical electron from decay would be stopped by a piece of aluminium a centimeter thick, half a centimeter thick, something like that. Then the gamma ray, which isn't charged at all and is very high energy, typically makes it quite far through matter. So if you wanted to stop a gamma ray, you'd need thick lead on the order of, say, 3 inches or so. But even then, the gamma ray can still knock electrons out of the lead that come out the other side. Now, all types of radiation can be dangerous because they can ionize your body. They can cause damage to your DNA.
The question we have to ask ourselves now is, what is the danger to human beings? Should we be exposed to excessive nuclear radiation? How much of it is too much? And how is exposure measured and monitored?
If you have a sample that's radioactive, then you measure its activity in a unit called becquerels, which is a small unit. It's the number of particles, decay products per second, as opposed to the curie, which is the old unit, which is a very big unit, and that's the amount of activity in 1 gram of radium. So that was a very big unit.
Becquerel is named in honor of Henri Becquerel. He was a French scientist who actually first discovered radioactivity from natural sources. And 1 becquerel is equivalent to 1 nucleus disintegrating per second. Another unit that is very often used is the curie, and the relationship between the two is that 1 curie is something like 40 billion becquerel. So curie is a very big unit of radioactivity, and becquerel is used for more low-level radioactivity. I also want to discuss the linkage between the source, as it were, and then the effect on persons. And that is done via the concept of dose. Dose refers to the amount of energy that is deposited in a particular mass of, say, human tissue. So that is normally given in the unit of gray.
The gray is a unit which measures the amount of radiation absorbed. Specifically, 1 gray is 1 joule of absorbed energy per kilogram of matter. And this applies to any matter.
We have different types of radiation. We have alpha particles, we have beta particles, we have gamma rays, and each of these different particles have different effects on human tissue. So they have different biological effects. Because of this, you actually have to weight the contribution of the different radiations to work out the total dose to, for example, human tissue.
But if we look at living matter such as plants and animals, and humans specifically, then we use a unit called the sievert. Now you multiply the gray by a factor which takes into account the type of radiation. So a high energy alpha particle will cause more damage to a living organism than an electron or a photon. So it will be assigned a higher weighting factor. Then you also wait for the organism in which the radiation is absorbed. So insects and plants can survive radiation much better than animals and mammals. So we'll have higher multiplication factors. And then for your parts of your body, like your hand, will have a lower multiplication factor than your chest because it's more sensitive to radiation. And so it's more complicated to work out, but the sievert is a better description of the dose of received radiation and what effect it will have on you biologically.
So if you take your absorbed dose and you multiply it by what we call a quality factor, you then get what we call an equivalent dose. And annually, the equivalent doses are of the order of 3 millisieverts per year for the general population.
I have a sketch that shows how the background radiation is contributed. 55% is due to radon and its progeny. Radon is a gas and it emanates from the surface of the earth and also from building materials. Natural radiation is made up of terrestrial radiation and cosmic radiation. Cosmic radiation is due to the interaction of cosmic rays from interstellar space with the elements in our atmosphere. Through their reactions, we have secondary cosmic radiation, which can reach the Earth. As you move higher by the altitude, radiation increases. So a person who lives in Joburg is more exposed to cosmic radiation than a person who lives in Cape Town. Also, if you you fly, because you go high, you become exposed to more cosmic radiation. The other radiation is terrestrial radiation, and it contributes 8%, and it's made up of natural radioactive materials which were created at the beginning of the Earth. Under man-made, we have products which contribute about 3%, and these are from smoke detectors, for example, and television and computer monitors. 11% is from medical X-rays, 4% is from nuclear medicine. The other 11% is internal radiation, that is the radiation coming from us as human beings. Now, radiation has to be measured. We can measure radiation with radiation measuring instruments. And one of the people who invented a radiation measurement instrument called an ionization detector was Geiger and Müller. And I have a diagram that shows how the Geiger-Müller operates. You have your Geiger tube, and inside it's air, or you can use a gas. It is connected to a voltage. It's got electrodes. The one on the center is the anode, which is a positively charged electrode, and the shell is used as a negatively charged cathode. It is connected to the voltage supply. When an incident ionizing radiation enters the tube, it causes the electrons of the atoms in a gas to ionize. It removes the electrons. And these electrons, when you apply the voltage, an electric field is created and they are collected onto the anode, and you can get a signal which can be read out in your circuit. And this is an example of a detector which operates like a Geiger-Müller, and it's here, that's where you have your tube with a gas inside. As you approach your source, the sound will increase, telling you how radioactive the source is. When you work with radiation as a worker, you will be given another detector which is separate from a readout. For example, here I'm wearing a detector. It's a dosimeter. It's a TLD. TLD stands for thermoluminescent detector. It's got a thin strip inside made of a special formulated aluminum oxide, which luminesces when stimulated with a laser light. And the light that is given off is proportional to the radiation that I would have gotten exposed to. Now, if you regularly work in a room where there is radioactivity, you are issued with a dosimeter like this one. It's called a EPD. EPD stands for Electronic Personal Dosimeter. When you work in your area and you approach a source where the activity is very high, it will give you a sound, an alarm will go on, and then that means you have to get out.
In terms of radiation, there are two effects that come out, and one is what we call effects that you can see. If you're exposed to a very high dose of radiation, you will get what we call deterministic effects. For example, you will see a scarring of the skin, a burning of the skin. In the case, for example, of the Chernobyl workers who cleaned up after the Chernobyl accident, a lot of them got severe central nervous system disorders, diarrhea and so on. So those are the deterministic effects, very, very high doses. That's the one type, and the other type is what we call the stochastic effects. These are effects that manifest themselves after a very long period of time, and it's got to do with damage to the DNA in the human cells. Because of the damage inflicted by the path of the different types of radiation through the cell, you can upset the DNA, you can actually damage it, and that causes the cellular repair mechanisms to be impaired. And you can then get a situation where you have a runaway growth, for example, and that manifests itself as cancer, normally after a very long period. So that's a stochastic effect.
As in an atom, the human cell has got a nucleus. The difference is that this nucleus is made up of chromosomes and not neutrons and protons. And the nucleus is surrounded by a cytoplasm instead of the electron cloud in an atom. When you irradiate that human cell, the radiation damage specifically targets the nucleus, which contains the DNA. And that DNA is a very important genetic material. And if there is any damage in it, then you would then have adverse effects. So we've got a number of ways of seeing this damage using some laboratory techniques, including high-powered microscopy. You could then grow the cell to get into a state that we call a metaphase state. And that is the state when the nucleus breaks apart and all the chromosomes are left free. The free chromosomes can then be stained specific for particular chromosomes to see if the radiation damage has been caused in any of them. That broken piece of chromosome, because of radiation, would then not have that particular apparatus for sensing the poles during cell division. Radiation damage depends on the dose of radiation you give. If you give a small dose, as in this case 1 gray, you would get a lower level of micronuclei. And here we have an example of 1 big micronucleus at 1 gray of radiation. On the other hand, when the dose is increased to 4 gray, we do see an extensive level of damage. And in our case here, we have 5 micronuclei in that particular cell.
The great irony seems to be that the properties that make radiation so dangerous also make it very useful. Almost as soon as it was discovered, the possibility of using radiation in medicine was obvious. In World War I, Marie Curie took mobile X-ray units to the front lines to find shrapnel fragments and inserted radon gas tubes into wounds to destroy damaged cells to prevent gangrene from forming and spreading. Today, safer alternatives to radium are used, but for very similar treatments.
There are 3 major ways of treating cancer, that is surgery, chemotherapy, that is treatment with drugs, and by radiation. With radiation, we use different types of methods, or different types of particles or beams, if you like. The most common one being X-rays, which is used in just about every hospital and clinic in the world, and electrons, which is also used in many places, and then the more exotic types of particles are the nuclear particles, neutrons, protons, and even what we call heavy ions, that are ions which are heavier than protons. There are very few places in the world that can do these nuclear types of radiation. For example, for neutron therapy, our facility here is one of only 8 in the world. And of course, it is also the only one in the Southern Hemisphere. With proton therapy, there are at the moment about 25 operating facilities, of which we have one here, of course, and it again is the only one in the Southern Hemisphere. The reason why radiation is used for treating cancer is that it turns out that growing cells are very susceptible to radiation damage. And cells which are so-called, let's call them sick for a simple, to explain rather simply, are more susceptible than healthy cells. There are many different types of tumors that occur, and some of them are much better treated with, for example, neutrons than others. These are largely very large tumors which are slow growing, which are not susceptible or not as susceptible to conventional radiation, which are, in this case, X-rays and electrons. The use of protons and other charged particles is to treat tumors which are very close to critical structures, which can easily be avoided with these types of beams and cannot be avoided with X-rays and electrons. Yes, you damage the DNA in the tumor, or you kill it in fact, or by destroying the DNA. And of course you really have to kill all the cells in the tumor, otherwise they can proliferate again and start growing. So it's essential that all the cells are destroyed. It doesn't matter what dose you deliver to the tumor, you can deliver an infinite dose and you'll kill the cells. You may not need to do that. But the limitation in all radiation therapy is the damage to normal tissue. And all tissues have certain tolerance doses which are well known, and you have to keep the total radiation to the healthy tissue below that dose, otherwise you will have problems. But these things are known, and one can design the treatment in such a way that you actually spare the normal tissue. But nevertheless, you do sometimes get normal tissue damage. And that is probably the biggest problem in radiation oncology. And the other applications of nuclear techniques in medicine are largely in diagnosis, using radioactive traces in the human body from which one can detect usually physiological functions or abnormalities like cancer, for example.
Radioactivity is used in diagnostic medicine predominantly as a radiopharmaceutical. That would imply using a radioactive material in small quantities connected through to an organic compound, which is generally in liquid form, and that will be injected in through to a patient. The patient, should they have cancerous or even non-cancerous tumors, it will show up on a screen such that the radiologist or the doctors involved will be able to see it as a hot spot on a screen.
As is the case with so many concepts we use to describe radioactivity today, it was Ernest Rutherford that came up with the equation that describes the rate of decay of radioactive nuclei with regards to what he called its half-life. The half-life of a radioactive isotope is the time taken for half the nuclei present in any given sample to decay, or the time taken for the activity, measured in becquerel, of any given sample to fall to half its original value.
As early as 1905, Lord Rutherford realized that you could use radioactivity to date rocks. Naturally occurring isotopes in rocks, for example, uranium-235 is one of the most famous, decays with time to form a daughter product, and that all natural products contain these radioactive elements. What they then realized, that if you understood the time taken for uranium-235 to decay to lead-207, which is its daughter product, if you understood that half-life, you could measure the amount of parent, that is uranium-235, and you could also measure the amount of daughter product in the rock. If you knew the half-life, you could calculate the age of the rock. And by 1950, the concept of dating rocks was well established, and geologists throughout the world were building laboratories to date rocks. Now, not all rocks can be dated. It's only volcanic and igneous rocks that are dated. To give you an example, if you have a volcanic eruption, the uranium in that rock will all be in the form of U-235 at day 0. There will be no daughter product. But once the rock cools and solidifies, the uranium starts to decay from uranium-235 to lead-207 according to the half-life of uranium, which is 704 million years. In other words, if you have a gram of uranium-235 in the rock, it will take 704 million years to go from 1 gram to half a gram. At that point in time, you will have half a gram of lead-207, the daughter product. And that is how the concept of half-life and radioactive dating works. There are many radioactive elements in the periodic table. Now, all these elements have different half-lives. Some have long half-lives, measured in millions of years, whereas others, such as carbon-14, has a relatively short half-life measured in years, 5,730 years for carbon. The net result of these different half-lives is that you can use the elements with long half-lives to date very old rocks, whereas you can use carbon-14 to date very young material. For example, if you want to date dinosaur bones, you use carbon-14 because the dinosaur bones are relatively young. How old is the Earth? What we find is that we really don't know the age of the Earth because the Earth is a dynamic system. On Earth, because the Earth is dynamic, those rocks are continuously being destroyed by volcanoes, erosion, and most importantly, plate tectonics. The oldest rocks, some of them found here in South Africa, are about 4 billion years old. When we look at the rest of our solar system, what we see is that the other planets are all covered by meteorite impact craters. That's because the other planets in the solar system have not changed since the time of conception. It's only Earth that is dynamic and has been continuously changing in time. And what we find is that no matter what material comes from outer space, be it the moon or meteorites, they all have the same age, that is 4.5 billion years. By conjecture, we know that the starting point of the Earth is about 4.5 billion years. The theory behind radioactive dating is simple. The process is in fact quite difficult, and the measurement of radio elements in rocks is fairly difficult and complicated, and one has to build sophisticated machines such as mass spectrometers and accelerators to measure the amounts of radioactive material in rocks very precisely. And the accuracy of the age of a rock is dependent on the accuracy or the precision by which you can measure the amount of radioactive material in rocks.
By the 1930s, when Hermann Joseph Muller published his research on the genetic effect of radiation, for which he received a Nobel Prize in 1947, the initial enthusiasm about the industrial and technological applications of radioactivity was largely tempered, as it became more and more evident that serious consequences accompanied the uncontrolled use of radiation and radioactive substances. In the last 50 years, many debates have raged about human activities involving the use of radiation that increase our exposure to background radiation. Perhaps our approach to the use of radioactivity should be guided by the following quote from Albert Einstein. Concern for man himself must always constitute the chief objective of all technological effort. Concern for the big, unsolved problems of how to organize human work and the distribution of commodities in such a manner as to assure the results of our scientific thinking may be a blessing to mankind and not a curse.
Yeah.